I changed the plan of things. We were to look at Z transform, and I thought for 2 reasons I'll change that. We look at maybe a topic which does not require much explanation, is more self-explanatory. We get out of our way, and also, of course, we had a heavy lesson in the morning, so probably I jumped the line and went to a shorter and a much lighter topic, which may require less explanation, so I don't need to write anything. So we are going to look at baseband transmission systems, and there is so much to baseband transmission systems, but we're only going to look at certain aspects of it, because it is asked for in the syllabus, but there is so much to it. So we look at the aspect of line encoding and ISI. So I hope you are all able to see the my presentation. Yeah.
Yes.
Very good. This is a topic we can we can go through in 1 hour, and so that now that we have started with this, I think I'll cover this, and then next time I'll cover the passband transmission systems before we go back to the Z transform, because the Z transform will continue up to the filters, and so actually it's a good idea to get this out of the way. But normally I put it at the end, but I decided just to change it to today, and let's see how it is. So baseband, when you talk of baseband, a good example of baseband is a PCM, as a digital baseband system. It's a system in which you don't modulate a carrier. In fact, generally, whenever you talk of baseband, you are talking about operating from 0 to some frequency F. But when we talk of the carrier modulation, we are normally talking about a frequency F1 going up to F2, and F1 is not 0, so it is just a passband somewhere far from 0. Yeah. So
excuse me.
Yeah.
Could you kindly zoom into the presentation?
Oh, it looks small in your side there.
Yes.
I think it's because I'm using wide screen, so it looks big. Let me zoom it. Let me make it bigger. Okay, I'm the one who it should be. These are the pages. The zooming. I'm the one who zoomed it. So that it fits. Usually, my workstation has have 2 different screens. So here it is. Is that better? That's 100%.
Yes, it is. Yes. Thanks.
Yeah, thank you. So in PCM, PCM is actually a step, is a next step from PAM. PAM, that is pulse amplitude modulation, is what you get when you sample, and PCM is what you get when you encode into each of those samples into a digital word, and depending on the level of the quantization noise which you want to endure, you decide how many levels you're going to have. Yeah, because depending on the levels, the quantization noise will be more when you have fewer levels. You have more levels, it reduces quantization noise. So if you have more levels, then you need more bits. Yeah. So we are going to look at how you represent those bits as signals for transmission, as opposed to the passband, which we are going to look at, whereby the bit, although again, when you see the bit, it is still a signal represented by a bit that modulates the carrier. Because remember, the carrier is a signal, so you have to modulate it with another signal. So you actually still use binary, I mean, line encoding. Actually, what we are discussing here is called line encoding. When you transfer, I mean, when you represent a bit with a signal, we call it line encoding. And even in digital communication systems, as we are going to see later, we actually do use line encoding, because you're going to see that the modulator itself is operated by either non-return to zero, which we are going to discuss here, or return to zero. Yeah, to modulate. The modulated signal will be a non-return to zero signal. Yeah, which will have been produced to represent bits 0 and 1. Yeah, we'll see that, but let's first of all look at what these alternatives are. So generally, for baseband transmission systems, digital baseband transmission. Again, you have to be very careful. You talk about digital. The higher level represents a bit 1, and the lower level represents a bit 0. So we are going to look at various encoding schemes and how you select an encoding scheme. What do you look at? The obvious one of the first one is the ability to eliminate DC component to enable AC coupling. What you're saying is there will be AC coupling in the system, and if you have DC power, it will be coupled. So you use too much power, but you're not able to deliver that power to the other side of the transmission line. So you need good AC coupling, and therefore we need to eliminate DC. We want to eliminate the average amplitude, average voltage. Yeah, average DC is what we are talking about. So that is a property we require from an encoding scheme. Another important property is self-clocking. We like a self-clocking encoding scheme, like Manchester. When you say as an encoding scheme, it means there is a transition. Remember a clock transitions at every time, at every period interval, at every interval of that period, which is normally a period. Yeah. So you need a system that transitions at every interval. Yeah. And Manchester encoding does that. So Manchester encoding will be a good example of an encoding scheme that does self-clocking. So self-clocking is important because you can regenerate the clock that was used at the transmitter at the receiver using your received signal. Because ordinarily, if you didn't have that, what you'd need is another line carrying a clock to synchronize the transmitter and the receiver. That's why these encoding schemes which can do clocking, which can recover the clock, which have the clock inbuilt into them, are actually very important. So that is used for synchronizing. Then we need bandwidth efficiency. Some schemes have better bandwidth than others. Actually, what it means here, especially for baseband schemes, as opposed to passband. In passband, when you talk of better efficiency, probably you're talking about being able to carry more bits within one symbol. So you have different symbols carrying different bits. So you have symbol 1 carrying, for example, if you are transmitting for QPSK, which we are going to look at, you are transmitting 2 bits. So you have symbol 1 carrying 0, 0, symbol 2 carrying 0, 1, symbol 3 carrying 1, 0, symbol 4. So you need 4 symbols to do that. You need 2 symbols. But when you talk of bandwidth efficiency, when it comes to line encoding, we are probably not talking about that, because remember, you can still do it. You can carry more bits using different sources with the different amplitude. But I think, as I've mentioned several times, is systems that you should encourage in transmission, because those are the choice. So that's not encouraged. Yeah. So you find most bit-bus systems just carry one bit with one board. One symbol carries 1 bit. Some actually now use 2 symbols, 2 transitions to carry 1 bit. Yeah. So the ones you discuss, you're going to find some of them are actually having 2 transitions for 1 bit. And that is spectrally not efficient. Ideally, you should carry 1 bit with 1 transition. So if you're going to do 2 transitions to carry 1 bit, that is considered spectrally inefficient. Yeah. Mainly that's what we'll be looking at when we talk about bandwidth efficiency with respect to line encoding schemes. Yeah. Differential encoding. You want a system whereby if the wires are inverted, because again, it's just telling us that normally with the baseband, we are using wired systems. So you are going to find Manchester is used by Ethernet. Ethernet uses Manchester encoding. We call it the IEEE 802.3 encoding. Manchester encoding as opposed to the GE Thomas. We are going to see the 2 of them. So there is one which is specifically called IEEE 802.3 encoding scheme. So Manchester is used by Ethernet. So well, I only mentioned that to mean that normally we use it for wired systems. But again, we are not even using differential. I mean, in Ethernet, we are using Manchester. So we are not even thinking about wires changing, because, well, for data communication in a LAN, it's unlikely that you're going to change the wires. Yeah. You have 8 pairs. So you're not talking of 2 hours. I mean, you have 4 pairs. So that's why we don't have to think about using differential encoding, because differential encoding also is also a bit complex. It better, but it's the receiver and the transmitter will be a bit more complex than when we are using the other simple voltage level or just a change. Yeah. Noise immunity, of course, some encoding schemes have better noise immunity than others. Obviously, anything that relies on the absolute value of the signal has less immunity against noise, because noise is additive. White noise is additive. So the ones which, for example, just rely on a transition either from high to low or low to high, have immunity. Than the ones which rely on the level of the voltage. Yeah. So let's look. So encoding schemes broadly fall into these categories. The first one is non-return to zero. Actually, that's a group of non-return to zero we are going to look at. Then there is a return to zero. And there is phase encoded by phase. That will include Manchester and differential Manchester. And then there will be multi-level binary. We are not going to level binary. As I said, this is another system, but we are going to limit ourselves to these three types. Not for any reason, just to make it shorter. Yeah. I just chose to not to discuss everything in this band, because this band again is a whole course by itself. So I find myself when you have so many things in a syllabus, there are some things you are unable to go into certain depths. So we left out the multi-level binary, but we are going to look at these three other types. Non-return to zero, a high voltage or non-return to zero level, NRZL. A high voltage represents a 1, while a low voltage represents a 0. Yeah, that is the signal is encoded in the levels. Then there is NRZM. This means NRZ mark. It's also in some circles called NRZI, NRZ invert. Yeah. And in this one, NRZM bit is represented by a transition in voltage. So you're saying there's a transition when there's a one bit, and no transition when there is a 0 bit. So 0 bit is represented by no transition, when a 1 bit is represented by a transition. And this transition means wherever you are, for 0 bit, you transit. Doesn't mean, unlike what we are going to see in Manchester, whereby in one case you are transiting from high to low for one bit, for one type of bit, whether it's either 0 or 1, and then you're going low to high for another bit. This one you're saying you transition wherever you are. That's why we call this a differential encoding. It does not matter. Polarity doesn't matter. Only the transition. Yeah? Only it doesn't matter you are transiting from where. Whenever you transit, we know you are transmitting a 1. When there is no transition, you are transmitting a 0. It doesn't matter whether you are where you are. You see, it doesn't matter whether you are high or low, but it doesn't matter whether you're, I don't know which is the best way to put it. It's different from Manchester, because Manchester high to low means, depending on which Manchester, it could mean 1 or 0. And low to high could mean 1 or 0, depends on the Manchester. But for this one, just transition is what encodes the signal. So transition means a 1, no transition means a 0. Then of course we have NRZ S. S just means space. Space is just opposite. It's just opposite of mark. So whenever you use S, we are saying is a complement of mark. These names came from the Morse code, which was among the earliest digital communication system. Because we were transmitting marks and spaces. Yeah, in fact, Morse code started the mark was some beep, and the space was no beep. So you beep. Now the length of that beep and how many beeps follow one another was interpreted as a certain message. I'm lucky to have seen those systems. Actually, I saw those systems in application. They were getting, when we joined the organization, we joined, they were still communicating with some Morse code. And they were facing them out. Actually, we are the ones who faced them out. When we went there, I mean, we were being employed because they were changing the systems to the new systems. Yeah. So that's where the mark and space come from. We still use it today. So NRS is a complement of NRM. Complement just means if NRZM for bit 1, there's a transition, it means for S, for bit 0, is a transition. Let's progress. So here you are. This is your zeros and ones, the sequence of bits. And 1 is represented. We are starting at 1. Sometimes it may not be, but we are starting at 1 for 0. Okay, for this case, it's straightforward because 1 means positive level and 0 means negative level. And please, if you are ever given something like this and you are told to do the waveform for a particular encoding scheme, always remember to write whether it's positive or negative. Otherwise, you do that, you don't do that, you are wrong. Because now, if you write this and you don't put this, I don't know whether yours is NRZ or what you are going to say next, the RZ. So it's important that if it's NRZ, then you have negative and a positive. If it's RZ, to be positive and 0, return to 0. Okay? So that is that. Then this one is the NRZ invert. You can see you are inverting on 1. Yeah. So you had started here. You started with the positive. This was a 1. You started with positive, but since a 0 was coming, you did not change. You did not invert. A 0 was coming, you did not invert. A 1 was coming, you inverted. A 1 was coming, you inverted. 0 is coming, no invert. 1 is coming, you invert. This is the opposite. We have started at negative. Yeah, this one, depending on each system, you find that whenever you have, irrespective, sometimes it doesn't matter what signal is here. We start the NRZ level with high. Yeah, this one we start with low. No, I think this one. This one we always start according to the level. Here you're going by a level, but this transitioning type, it will start at one side. And normally this NRZ inverter will start at positive and this will start at negative. And depending on what comes next, it is going to act accordingly. So like this one started here. So we are going to 0. Remember, this is a complement of this. We are going to 0. So you change here. And here we are going to 0. You change again. 1, no change. 1, no change. 0, you change. 1, no change. So that is, these are the two. That's the NRZ. If you have a question, you can kindly ask. You can always post on the chat. Or just press your microphone and talk, or raise a hand. All those are acceptable in my class, not all classes. Mine you can talk and you listen. I think it's because not many people ask questions, so we give that freedom. Whenever you want to talk, you can talk. So the next one is return to 0. Yeah. This one there are two. There is the unipolar return to 0 and the bipolar return to 0. So unipolar just has a half-bit wide pulse, or the absence of the pulse represents as 0. This one has 3 voltages, it has only 2 voltages. Yeah, this one has 3, and ones and zeros are represented by 1/2 bit wide opposite level pulses. So bipolar RZ, we have opposite level pulses, but we are going to see there are 2 versions of bipolar RZ. So here they are. Unipolar 0 is unipolar, it goes to one side. So that is a half pulse. And you can see this one. If, for example, there are ones following, it would go like this, go like this. So actually, this will be spectrally inefficient. Yeah. Yeah, because you'd be having 2 pulses representing 1 bit. Yeah. It will be actually more spectrally inefficient compared to this NRZ. You can see there are less changes. This one is spectrally more efficient than this. Yeah. So that is unipolar RZ, this is bipolar RZ. Now the standard bipolar RZ goes, the half pulse goes up for 1 and half pulse goes down for 0. So this is 1, 0, 0, 1, 1, 0, 0. Yeah. That is bipolar RZ. Then we have what we call a return to 0, AMI, alternate Mach inversion. So this one you are inverting on Mach. As I said, we have carried Mach to mean a 1 and a space to mean a 0. So this is alternate Mach inversion. You are inverting on ones. Yeah. So you get a 1 here. This is a 1. So this must be, remember, this was 1, 0, 0. We can deduce what this is from this waveform. So when you have a 1, you have that. But when you have a 0, nothing, 0, nothing. You see here 0 was represented by going negative. Yeah. But here 0 is nothing, nothing. But the next one goes down, goes in the opposite direction. The next one, doesn't matter when it's coming, it goes opposite. Yeah. This avoids a situation whereby you could be having just too many ones. You end up having a lot of DC. Or you have too many zeros and you get out of DC. And this, maybe you have too many ones and you get out of DC. This one, it doesn't matter whether it is just once. You are going to get same number of ones going up. So the resultant DC is highly reduced. And of course, this return to zero AMI, there is a version of the same one called pseudo-ternary. Pseudo-ternary just means you are inverting on zeros. Yeah. I think here it is. So it's a complement of AMI. So you are inverting on zeros. This one you are inverting on ones. Here they are. So that is return to zero and the next one. Yes, Sherry.
What do you mean by indicate negative and positive? You said something about us having to indicate negative or positive. What exactly were you referring to?
Indicating positive and with respect to these waveforms.
Yes.
Okay. I was saying, you see, these are signals representing zeros and ones. I think up to there we agreed. But we are saying that for this, one is means a positive half pulse. Zero, no pulse. No pulse. I don't know. I'm hoping I'll answer. I don't think that's the question you asked, but I'm hoping explaining this, I'll answer your question somehow, because I did not get the question very well. So that is 1, this is 0, 0, 1. Well, I've not written that. What I was saying is, I think I get where your question was. I had not put the ones and zeros here, like I had here. I didn't put this, but I'm saying, just looking at this RZ, it means this must be a 1, just from the RZ. This is a 1, this is a 0, this is a 0, this is a 1, a 0, a 1. So we assume all these other waveforms are following the same here. That's why I was talking about indicating. Yeah, I think that's what you're asking, isn't it? Did I answer your question?
Yes. There's a part you mentioned something about indicating positive or negative. Was it the
Oh yeah. Now I get it. I get you. Is here. You see, this is unipolar RZ. Now, if you are asked to plot or to sketch a waveform or a specific line encoding scheme, it's important that you indicate what is positive and what is negative? I think that's the question I said, because if you draw this and then you don't put whether it is positive or negative, I will not know whether you are drawing this, for example, and oh, the other one is this one. This, you see, this is positive and this is negative. So 0 is in the center here. So this is called non-return to 0. It does not return to 0. It is either positive or negative. It does not land on 0. So why I was saying that is because sometimes people, you're asked to do N or Z, and then you draw without putting this. Now, it will not be very clear that you are doing, okay, that's a have a pulse, but it will not be clear whether you're doing this or, or you're doing this. That's what I meant. It's good to put positive, plus, and minus, plus and minus. Because this plus, this has no minus, is 0. Because this is unipolar. That's what I'm emphasizing, because I see it a lot, maybe in an exam situation, somebody is told to sketch, and you just sketch without indicating where the positive and negative is. I think that's what you're asking, isn't it?
Yes, yes.
Okay, thank you very much. I think I answered your question. Yes? What systems are you working on that? Oh, I see there's a... Were you working on that or using Morse code? Oh, that's an interesting... what was the encoding scheme for Morse code? Okay, the system... yeah, that's an interesting question. Actually, I made that system. It didn't stay long after I joined. I did work for Kenya Railways for some time. So the communication between stations used to use those beeps. Well, it was not exactly the original Morse code, but it was based on the same system. And I think the encoding was not more of 0 and 1. It was certain beeps followed. If a certain pattern, well, it's the same concept today. If you have got maybe ASCII, actually ASCII is kind of almost based on the Morse code. Yeah. If you have ASCII, then you are going to have 1 0 1 0 1 0 0 0 1, maybe 7 bits representing a certain character, and another combination of the same bits, or the same 7 bits representing a different character. And Morse code was working on the same basis, that the length of your beeps, which beeps follow which beeps, would have a certain meaning. And I was also lucky. I met, by the way, I met the same system in Chiromo during my first year, because the computers then, that's quite some time back, the computers then were still using those perforated cards to carry the messages. So what the computer was doing, to just having some light shining on the cards. They were called punch cards, actually, on the card, and there will be sensors, and depending on where the holes are, it is going to send something different. Yeah, but it's a good question. What system was I using? What was the encoding scheme? It wasn't much of an encoding scheme. Yeah, but I was mentioning it because we still use those words today, the mark and space. It was being used even during the war. During the war, this actually, that fellow called Morse, I don't know, I think it was the first one. I'm not sure of the history, whether it was him or Graham Bell. Oh, Graham Bell came with the telephone. But the one who first awarded the transatlantic communication using electronic communication, I think was Moscow, was Mos. Yeah, but again, I can't remember my history. I've read it many times, but I'm not. But yes, I met the system working, and I used to be amazed when I go to the stations. I find that guy just listening to the beeps, and he understands what the message is getting. Yeah. Did I answer your question? Except for the encoding scheme, they are not using any of this.
Yes.
Okay, very good, very good. So the next encoding scheme is the biface encoding. So this biface encoding, we have Manchester encoding, also known as biface level. So we either have biface level or biface mark or biface space. So biface encoding, which is known as biface level, is this one here. I can just show how it works. Here it is. So there are two biface level. Well, there are many, but the others are just variants of these. One is the Manchester. Manchester comes in two variants. That is the IEEE 802.3 convention. This one is used by Ethernet 802.3. It goes by the same name. That is wired Ethernet. Wired Ethernet is IEEE 802.3. So the Manchester that is used by Ethernet, wired Ethernet, whether it is Ethernet or fast Ethernet, is this Manchester IEEE 2.2 convention. I think it got its name from that from Ethernet, which of course IEEE 2.3 is a committee of IEEE that was dealing with that particular protocol. Yeah. So in this Manchester 802.3 convention, one is going the signal goes from negative to positive. That transition from negative to positive is what represents one. And moving from positive to negative presents as 0. So negative to positive, positive to negative as 0. Then you can see there is no transition in the middle. There may be no transition at the edge of an interval, at the beginning of an interval. But there is always a transition in the middle of the interval, because the transition has to be in the middle of the interval, representing the signal. And whichever signal it is, there will always be a transition in the middle of the bit interval. Yeah. So that is 0, that is 1, that is 1, that is 0, that is 1. So this one is that Manchester. The other Manchester is called G.E. Thomas Manchester encoding. G. Thomas is just the opposite. So this will be a 0, and this will be a 1. This will be a 1. This will be a 0. This will be a 0. This will be a 1. This will be a 0. That would be G.E. Thomas. That is the transition from low to high is a 0, and high to low is a 1. That is a G.E. Thomas convention. Now, differential works in a different way. There's only a transition when which one is this? I want to ensure that the transition is for bit 0. Yeah, because it can be for bit 1 or 0, but transition at the beginning of bit interval indicates bit 0. Yeah, this one doesn't have two versions. So the version is a transition at the beginning of the interval indicates a bit 0. No transition, a bit 0. So here we are. If there is no transition at the beginning, so here of course we have started from differential, we started from positive. So since we are talking about a transition at the beginning of the interval, we won't talk much about it here. So we will start from here. A transition at the beginning of the bit interval means a 0. You see, this is 0 coming, so there's a transition at the beginning of the bit interval. If a 0 is coming again, there will be, of course, the transition comes here. It goes back here. So the transition is from, there's a transition at the beginning of the bit interval, and then it comes back. There will always be a transition, again in the middle of the interval, just like here, but for different reasons. You see here, it was because that's a signal. But here, there's a transition in the middle of a very bit interval. So it doesn't matter where you are, you have to go to the other side in differential Manchester, in the middle of the bit interval. But at the beginning, will mean that transition will mean what you're going to get is a 0. Yeah. So you can see, like here at the beginning, because there's a 0, but you have to go back to here. At the beginning, that's a 0, but you have to go back. You have to change to the other side. So no, at the beginning is a 1, no transition. Then you have to change to the other side. You always have to change in the middle of the bit interval. So following is a 1 at the beginning, no change. Then there will be a change in the middle of the interval. Then there's a 1, change, go back. Then here 1, no change. Interesting. It's an interesting encoding. So this is a differential Manchester. It will not matter if you change the wires, because at the end of the day, it is whether there is a change at the beginning of the interval. The changes in the middle of interval are purely for clocking and are not used for carrying the message. Yeah. So as I said, that's a simple topic. That's one aspect of baseband communication system, and I'll say again, is a wide topic. So I'm only looking at two aspects of it: the line encoding, how you encode in baseband, that's digital baseband communication, and we are going to look next at this phenomenon called intersymbol interference. So any question on this first, because I think we have reached the end of this biface. Any problem with the biface? So if everything is okay, then we can I know it's a strange hour, people are tired, but I think this is a simple topic we can finish before 5, so that we can get into another topic next week. Intersymbol interference. I've just drawn this diagram here to show you exactly what happens when a symbol is moving from, because remember this is a symbol. When it's input into the system until it arrives to the receiver, because this will be your symbols. These are the transfer functions representing filters at every point. So the first one, of course, will be the transmitting filter. So that we'll look at this again when you are doing the matched filter receiver and the coordination receiver. We are going to look at this again. So you have that. Then normally the signal which just comes from it's conventional to call it ST. It's interesting that you are dealing with the ones and zeros, but normally the symbols we deal with them as analog signals. Yeah. So this is ST. Then you have another filter. This filter is simply the channel. The channel itself has some filtering characteristics, and apart from that, also adds noise. Yeah, NT. And then after that, we have the RT. This is what you receive. And there's a receiving filter. The filter itself has got, the receiver itself is a filter. Then, of course, we do sampling at time T, period T. Yeah. What we are doing, we are trying to find out. Because remember, these pulses are at particular places. So what we are doing, you want to sample actually in the middle of the pulse. Yeah. You sample at the middle of the pulse to find out what is the voltage. And normally we are not testing just at the middle of the pulse. We are collecting the power over the interval. Yeah. The energy over the interval. So that depending on the energy you get, you can use energy because there's a time factor. Then you decide whether this was a 0 or 1. Yeah, so that is a sampler with some symbol timing. This one you generated. But remember this, you can generate this actually from if for example it's Manchester, you can generate that from the pulses. Yeah. And then sample. Well, to generate for the so you can get a part of that signal. As you can see, you're getting the part of that signal to generate the timing and then sample signal. Yeah. And then, of course, make a decision. That's why you're seeing this is YT is capital T. T is a period. Yeah. And the decision device decides whether it's a 0 or a 1. So that is how our signal goes. But I think somebody is trying to log in here. Of course, what happens as a signal is going towards the linear, it is affected by this, and it gets distorted. But for now, we want to deal not with just the distortion. We want to deal with the powers spreading out and affecting the subsequent symbol. Yeah, this is interesting because what we call intersample interference, there is interference in the time domain, and there's interference in the frequency domain. Yeah, both of them are called intersample interference. Yeah. So let's see what happens in the time domain. So, of course, intersample interference, just like things like what we have, well, just like the errors we can have in aliasing, where the spectrum is overlapping because you have not sampled at the Nyquist frequency. When those parts of the spectrum interact with each, or interfere with each other, of course, it will affect the time domain signal. Yeah, and it will introduce errors because the receiver will not be able to know which signal was transmitted. That's what we call errors. Errors is when you're expecting a 0 and you interpret that as a 1. And it can happen because of what is introduced by intersample interference. So one of the easiest easiest cause to understand of intersample interference is a multipath propagation. What it means is that when a signal is transmitted between points A and B, you can have the signal that goes directly through the line of sight and takes some time t. But you can also have another signal of a sample of the same signal that goes and hits a building and gets reflected in all directions. But one of them ends up going to the receiver for who the signal is meant. When that happens, because this one signal took a very long path, and we assume they are moving at the same speed, the speed of light, it means that signal, which took a longer path, will now interfere with the subsequent symbol that took the straight path. Yeah. And if the spacing of the symbols, if you have a long period, that may not be a problem. But when you begin having, when the bit rate increases so that you have pulses which are packed close to one another, then that spread in the time domain may affect that other signal which is behind you. So we are saying that this symbol that was ahead interferes with the one which was behind, but we are saying it is not the main one, it is the version that took a longer route of that signal ahead, interferes with the signal in the rear. That's what we call multipath propagation. Remember, multipath propagation is not always negative. We also use it for communication. When we have line of sight communication or near line of sight communication, you're actually using multipath. Because sometimes there is no direct signal that is coming to you. They are coming through reflections. You are not indirectly on the path of the BTS, actually like cellular. telephony. You're not directly on the line of sight of the BTS, but you still get your signal. That is multipath. Yeah. So it can be used if well harnessed or positively. Yeah. That's why you can be able to get your phone somewhere in the basement. That is actually an line of sight communication. Some of that is multipath. Yeah. So that is one cause of intersymbol interference. But actually it's not the biggest. The biggest is the band limitation, where you are carrying the signal. And why is it an issue? It's an issue because you're carrying pulses. Yeah? When you carry pulses, the Fourier transform of the rectangular waveform, of the rectangular pulse, is actually the sync waveform. Well, it's not sync waveform, it's sync spectrum. You have to be very careful. When you refer to the waveform, you're talking about time domain. Spectrum, frequency domain. So, if you do some Fourier analysis, you're going to find that waveform has got an infinite bandwidth, because that's what a sync pulse is. No, sorry, a sync waveform is. It goes feeding towards infinity, but it spreads theoretically from negative infinity to positive infinity. So that for one pulse interferes with one for the next pulse. Yeah, we also call it intersymbol interference. It's also an interference. Yeah, and that is because of the band limited channel. Yeah. So how the band limited channel comes in is because now the band limited channel is going to cut off that energy. So it has actually, you have interfered with the signal because you have cut off part of that signal. Yeah. It becomes a different signal. You have cut off some part of it. In the time domain now, that signal is completely different. In fact, you can think of it as it is now not going to be the square pulse. It will be something else that corresponds to that frequency spectrum. If you do the inverse Fourier transform, yeah, to get the signal, yeah. So, so we have seen that that is a cause, and of course, band limiting can mean two things. One is the channel you are allocated by the organization that controls frequencies. That is one. Number two, it can also be from the systems you are using. Some systems will have a frequency response that spans from F1 to F2. And your analysis goes from negative infinity to infinity. So that will also affect that. That's what we are saying is the limitation of the medium which we are using. And I think this is shown here. In the time domain, if you have this, in the frequency domain, you have this. Although what is interesting also, if you have this, the time domain, of course, time domain means this is not F, this is T. Then it's going to give you this in the frequency domain where this is F. Yeah. So if you have this, you get this, which runs from infinity to infinity, negative infinity, positive infinity. So if you have a band limited channel, actually what you should do, you should use this pulse. Not the spectrum, the pulse. You should use a sync pulse. If you want to use your band limited channel without any distortion, then what you need is a sync pulse. But a sync pulse is not realizable. So what we try to look for is, actually that's what we call pulse shaping. Because originally your pulse is a rectangle. You want to move away from the rectangle because it will give us a sync spectrum. So what you do pulse shaping. And what we are going to look is that you shape, you get a pulse that has got the minimum or requires minimum bandwidth. And that one, the one that will be the sync pulse. I think it's not practical. We are seeing here, if you remove your pulse, your you can actually, this is not remove. You can avoid ISI by pulse shaping. You actually avoid, because when you talk of pulse shaping, we're talking of pulse shaping at the transmitter. That if you transmit a sync pulse or another pulse or a class of pulses which we call zero ISI pulses, you can be able to get your pulse to the receiver without them feeling the pulse. But among that class of those pulses is only the sync pulse is not realizable. So we are going to see what is realizable. So there is a Nyquist. There's a Nyquist criterion. Some of us mistake the Nyquist criterion for sampling, but there's also a Nyquist criterion for zero ISI. And what we are saying is that zero ISI pulse PT must have this property. It is 1 for T is equal to 0. And 0 for T is equal to plus or minus TB, plus or minus 2 TB, plus or minus 3 TB, and so on. What we are talking about is this. It must be like this. Of course, this is a sync pulse does fit that, because this is a sync pulse. You see, the sync pulse is difficult to retrace, but this, you can see, these are 5 pulses, and these are the 5 pulses. Yeah, 4 pulses. The 5th pulse, when it is maximum, when it is 1, these others are 0. So this is the other pulse. Consider this in time domain. This is the other pulse. When it is 1, all these others are 0. When this is 1, these others are 0. Yeah. So we are saying it must be having 1 and zeros at these periods. That's the only way it will not interfere with others. You get it? That's the only way. So we are looking for that pulse that can do this. So sync function can do that, and actually is the ideal, but since it's not realizable, we go for the next best. That's the least cosine pulses, which satisfy the life criterion, but they require slightly larger bandwidth than a sync pulse, because sync pulse is the one that gives you the minimum bandwidth. But we can do with a risk cosine. Again, this cosine, you have to be careful. This don't like this, but please remember this is not the risk cosine. This is a spectrum of the risk cosine. It's not the time domain risk cosine. So it's not called risk cosine because it looks like risk cosine in the time domain, because it looks like risk cosine in the frequency domain. This is the risk cosine frequency response, which is the risk cosine spectrum. So the signal that gives you this is actually when you do the pulse shaping. That is the pulse you try to achieve, because you are unable to achieve the sync spectrum. Because not sync spectrum, sync pulse. Because sync pulse means what? It runs from negative infinity to infinity in the time domain. So you have to collect that pulse to transmit it for an entire eternity. That's why we say it's not practical. So, but this one can be used. Any question on this ISI? So we are saying you can do with ISI in two ways. One is preempted by pulse shaping at the transmitter. But if you can't, you can also remove it using equalization at the receiver. So equalization is the receiver, pulse shaping is at the transmitter. So apart from the other things we do at the transmitter, one of them is pulse shaping. If you want to avoid ISI, change the shape of your pulse. Or forget it and use equalizers to remove the effects of ISI. Yeah, and one of the most popular, there are many equalizer circuits, but one of the most popular is the zero forcing equalizer. And this refers to an equalization algorithm that applies the inverse of the frequency response of the channel. What you can look at this way as the inverse of frequency response of the channel. When you are designing is the inverse of that. So this method is called zero forcing equalization. And the ISI component of the equalizer is forced to zero. That's why you call it zero forcing. ISI component is forced to zero. Again, we have not looked at that circuit. I've just mentioned it for now. So are there any questions on this? Looks like we have come to the end of our document. We still have 10 minutes, but maybe we can use that to for any questions. But also, I think you can be sending your registration for the purposes of attendance. And again, next week, we are going to repeat. Actually, we will repeat for the next week after this. Yes, Samuel. Samuel,
Yes, thank you. I have a general question.
yeah,
Yeah, so imagining that you are working at Kenya Railways, and maybe at that time
yeah,
it wasn't so obvious that the telecom world will change
yeah,
to what we are right now.
yeah.
And so what did you do maybe to adapt to when let's say the world changed and we're now at 5G,
Yeah,
and what can we do, because you realize for us things might change, we might go to quantum stuff, and it might reach a point we might find ourselves having to adapt to a new environment. So if you reminisce at your time, what did you
yeah.
do to adapt to this fast changing world, the world of telecommunication? And was it so obvious at that time that things will be how they are right now?
Thank you. That's a good question. It's not that I didn't have to adapt, because by the time I joined the railways, they they didn't have engineers. I think I was among in my area. I think they trained only one cohort of engineers, and most of the training was done out of the country. So although our system was very behind, we okay. Of course, we were hit with two things. Apart from technology is changing, we are really behind in Kenya. So uh, that itself, I was already exposed to the modern technologies which were being employed elsewhere. Yeah, because our system was, even when I'm talking about, I'm not talking about it so many years ago. I'm just talking almost the turn of last century. We were still quite behind in the 90s, but and 80s, but the rest of the world was very far ahead. But of course, there was still also, even in those, even in that first world where we were going for the training, there were still changes. But I think it was more visible here. It was drastic here. I mean, especially now that for you, you don't have a problem because we are in this age of very easy to get information. You can imagine for us, even the library we were using was having books that were written in the 40s or 30s. Yeah. But what was helping is those courses which you are going outside. But for you, I think it's easy to keep abreast because information is easily available. So for you, I don't think in today there will be no problem. That's why we are in 5G. If it was those days, the rest of the world will be in 5G and will be in 2G. Well, that's the information you'll be exposed to. But I think for now, there will be changes, but I think you have access to the information. You have just keep on renewing your mind, renewing yourself. Yeah. And I personally had the interest, so it was also easy for me. But changes will always be there. You have to brace for them in the world of telecommunication. Yeah. But I'm seeing, of course, it may take some time. There has been so much change in the last 2 decades or 3 decades that we are not anticipating. I think change comes in quantums. We are likely to go maybe for another, maybe 4 or 5 decades before there is reasonable change, because we are trying to go to at higher speeds, but we are limited by the current technologies in terms of even materials and all that. That's how we are thinking now. We cannot even work anymore with zeros and ones. We have to go to quantum to increase speeds, because we have already reached the working with bits. We are already at the maximum, but with the quantum, with the qubits, you are likely to deal with much higher frequencies. Yeah, yes, there will be changes. I had not anticipated that, but I was a bit lucky in that aspect. Yes, Ogola.
Yeah, yes, I have a question concerning that attenuation that is normally realized when you are dealing with pulse-coded modulated signals for the satellite signals. Like, you always realize when it is raining, there is always that signal interference when you're dealing with TV signal. How do you think such a problem can be resolved?
The attenuation caused by, especially when it's raining.
Yeah.
Well, that has to be considered at the design stage, because you have to anticipate the rain. Because if you design your system assuming there's no rain, then your system will not work. Otherwise, you have to anticipate that there will be a certain level of attenuation when it rains. So even probably the spacing of your antenna, I mean how close the antennas are to each other, because we are talking about wireless communication. So you have to consider that. Then you have to consider also, you have to mitigate against that. Maybe even type of error control, because once you have interferences, you result of errors. So you have to have very robust error correction and detection methods. Yeah, that has to be considered in the
And not just rain, maybe there can be things like solar storm and electromagnetic pulses that can tend to interfere with the signal transmission, maybe for the wireless communication system.
Yeah, that might be difficult to predict. I think that one that's why you have even alternative systems, probably based on either wired or maybe based on non-terrestrial communication, like satellite, for those kind of times. But basically, you cannot design a system that contains, I mean, that there you may not be able to do. Yeah. Did I answer your question? But that's why we guys are there.
Yes, okay, sir. Thanks.
Okay. So thank you very much. We'll see you on Wednesday, and then Thursday we are going to have 2 lessons again, and then the next week, then now will be good. We have recovered the 2 weeks, so that we are covered. If the university gives us 2 more weeks, we are good. If they don't, we are still good. So have a good evening. Thank you very much.